Hello, this is Jack Jackson. We're going to continue our introduction to rotations a little bit with this video. Um, so we're looking at rotations. We introduced the concept last video using some older GeoGebra software, older Geometry Sketchware software. Um, in this one, we're going to focus a little bit about some resources in GeoGebra that can help us. So just recall that the definition of angle is the union of two rays with a common endpoint. So that is a set of points in our treatment of geometry. And we always measured an angle in radians with a number in the interval from 0 to pi inclusive, or in degrees from 0 degrees to 180 degrees. But when we get to rotations in geometry and also in trigonometry, calculus, it is useful to extend this idea so that we consider an angle as an amount of rotation that can have any real number as a measure. To make the distinction between these two uses of the word angle, we'll use the word angle as defined above as the union of two rays with a common endpoint as either just angles or physical angles, set of points, two rays with a common endpoint, and the measures between 0 and pi inclusive. And the amount of rotation then will be called the measure of rotation or a rotational angle. Could be any real number for a real number for a measure. Rotating in the positive direction is rotating counterclockwise. Rotating in the negative direction is rotating clockwise. Informally, the measure of a rotation is the assigned length of a path, arc length, taken by a pre-image point 1 unit away from the center of the rotation, and as that rotates around, it will trace a circular path or a portion of a circle or a circle and more than a circle, possibly. And the length of that rotation, how far it goes, as if you were doing, like if it was a car, it would be what your trip meter would say. You're on your odometer, or maybe you know a pedometer measuring your steps, measuring that way. In a Cartesian coordinate system of a plane, we say an angle is in standard position if one side is called the initial side is the same as the positive part of the x-axis, and then the other side will be then called the terminal side. And notice in particular that means the vertex of the origin. You can think of a rotation and sort of dynamically as sort of flicking that initial ray and having it spin around. Okay. And it turns out there are infinitely many different rotational angles which produce the same physical angle. Given an angle in standard position and the angle measure theta, then rotations of the following measure alpha generate the same physical angle. If you take it and rotate an extra 2 pi or integer multiples of 2 pi, rotating in either positive or negative direction, by an additional full circle rotation, that is an additional 2 pi, you get the uh, same physical angle, the same terminal side. Of course, the initial side is always the positive x-axis when it's in standard position. So if alpha is any theta plus 2n pi, where n is an integer, which is what this is saying, then that is going to be the same one. Okay. All right. And if the angle is above the x-axis, this angle theta is a measuring between 0 and pi, then you can think of that shortest rotation as a positive rotation, theta. If the terminal side is below the x-axis, the measure of the angle as an actual angle will be theta between 0 and pi. Then the opposite of theta will be the rotational angle that gets you there in the shortest amount. Again, adding multiples of 2 pi, integer multiples of 2 pi, will get you the same terminal side. So now we can, with that idea, we can now define the transformation called a rotation. A rotation about a point C, called the center point, by measure theta, is a transformation in which the image point A prime for a particular pre-image point A has the following conditions. The distance from C to A prime is the same as the distance from C to A. So they stay the same distance. The image and pre-image stay the same distance from the center point C. And the measure of the rotational angle um, is is uh, is then the theta. Okay. And so notice that to identify a particular rotation, you're specifying a center and a rotational amount or rotational angle. And so we use the letter R for rotation, and then we specify the center point and then the angle theta. So for example, you might have rotation 0, 0, pi over 4. So that would be rotating pi over 4 in the positive radians in the positive direction about the center of the origin. Therefore, the image of a rotation, informally you could call it a turn or spin, is formed by moving each point of the pre-image along a path formed by an arc of a circle centered at a given point and through a given magnitude of rotation, a rotational angle. Points move different distances, but the angle made by the pre-image to center of the rotation is the same as the magnitude of rotation. As the pre-image is placed into motion and this and moves from its original location to the location of the image, it always stays on a circle centered at the origin. So the distance from the center to the pre-image point is the same as the distance from the center to the image point. Okay, so let's illustrate that with a few different GeoGebra activities. This one was created by Janice Podgurski, one of my students, senior project students and former geometry student, and she did this as part of her senior project. So let's take a look at this one right here and use this to uh, generate some illustrations here. I'm going to open this in the app. Okay, so so it has some explorations here. This is showing you rotations here. So again, think of it starting. Notice that the initial ray is right here on the x-axis, the positive part of the x-axis, vertex at the origin. And as we take this going from 0 and spinning in the positive direction, we get this. Now, this particular illustration just shows rotations, positive ones from 0 to 2 pi, with the measures in radians there. This is set up so that you can do it with the slider, or you can put in a particular radian measure here. Let's say, for example, pi over 4. And there we get pi over 4, 45-degree angle there, for example. So how can we measure this angle? Step 1, we go out 1 unit on the positive x-axis there. We rotate that point along this right here, or about the origin like this. So think about flicking this and spinning. And then that arc length right there, this one right here from A to C, or from A to A prime, that is the angle measure for the rotation. When we take a circumference of a circle and divide it by its diameter of the circle, we always get the same number. That's pi. Turns out it's an irrational number. Since the diameter is twice the radius, we see that pi is the circumference divided by the diameter, or the circumference divided by twice the radius. So that is 2 pi r is the diameter, is the circumference. So pi is the circumference divided by diameter, or the circumference divided by 2r. Solving for circumference, circumference is 2 pi r. In this case, r is 1, so the circumference then is just 2 pi going all the way around. Okay, so we see that a rotation going all the way around would be 2 pi. Rotation going pi would be halfway. Pi over 2 would be the right angle then. Okay, because we're dividing a length unit of circumference and a radius unit of for the radius, those are both length units, like centimeters divided by centimeters. The units cancel out, and the angle measure of radians is technically not a unit. That's why when we write a number without anything, without this rad, it means radians. This is converting between angles and measured in degrees, minutes, and seconds. We've talked about this before. In degrees, we have 360 degrees for a full circle. And here we have it in radians. Just multiply by 180 degrees over pi. So we end up with degrees at the end. 180 degrees and pi are the same thing. So that's 1 for that fraction. So this stays the same value, but in this case, we can see it converted to degrees. Once we convert to degrees, we can subtract off the whole number part, that's degrees. The decimal part then, okay, we can multiply by, let me fix this. Okay, let's look at this example here. So to convert to degrees, minutes, and seconds, take the whole number of the degrees, subtract that off, take the still needs a so take the whole number of degrees, that's your degrees part. Take the decimal part, multiply by 60 minutes per 1 degree, because 60 minutes is 1 degree. This comes from the ancient Babylonian working at 60 degrees, base 60 here. And this gives you, in this case, 59 point something. Take the whole number part of the minutes, that's your minutes part, then take the decimal parts of the minutes and multiply by the 60 seconds over 1 minute. Notice that the minutes cancel out here, just like the degrees canceled out here. Degrees canceled out as leaving minutes there. The minutes cancel out here, leaving seconds. And of course, you can round this off if appropriate. So this is degrees, minutes, seconds way of writing it. This is a more ancient way of writing angles that is still used some today. Decimal degrees are very common, as are radians. Okay, let's continue to look at a couple of more GeoGebra things that are out there. Here's one that was written by Tim Brzezinski. So he has some text here, but let me go ahead and just open this in the app. So here we can see this rotating around. We can see it rotating. The measures are given in degrees that way, rotating in a positive direction or in a negative direction this way. Okay, so pretty simple but effective way of talking about that particular thing. Here's another one from the GeoGebra team. This one here talks about rotating points about the origin. So rotate this point 270 degrees clockwise. So what you want to do is move this, find the image here wherever you think it should go. Okay. So 270 is 3/4 of 360 degrees. It is 3 times 90 degrees. We're going clockwise, so we're going this way. 90-degree rotation would put it here. 180 would put it here, and 270-degree rotation should put it here. Oh, I was going, sorry, whoops, I went the positive direction, counterclockwise, and not clockwise. So we can try again. It should be down here. There we go. So positive is, clockwise is negative. and counterclockwise is positive. So 180 degrees counterclockwise. Counterclockwise would be this way. 180 degrees would be all the way over here. And you can check to see. And of course, you already saw what happens if you miss one. So you can just practice with this several basic ones. Notice that the distance out stayed the same. So if this was 6 out this way, it was going to end up 6 out this way. So I'll leave that to you to experiment with that a little bit. Here's another one from the GeoGebra team. GeoGebra team always does some great things here. So this has an isometric grid here with equilateral triangles for the grid instead of squares. And so here we can see this rotating around. Notice at this point right here, that vertex of the triangle is the center point. And see how far we're rotating in here. So that's 60 degrees or pi over 3 radians so far. Okay. But notice that it preserves the angle measures. This is 60 degrees. You can see that. That stays the same. That is half of 60 degrees. That's 30 degrees, as is this one. The 90 degrees stays the same. The lengths stay the same as well. Look at this going down here. So that as this figure is moving, rotating around, it gives it stays congruent. Lengths and distances, lengths, angles are all preserved there. This one we're predicting rotations around the origin. Let's take a look at that real fast. Okay, the point will be rotated 180 degrees counterclockwise around the origin. See, counterclockwise will be around this way, and it's going 180 degrees around. So let's see where's that going to be? It's going to be over down here somewhere. There should be a straight line going through it to its image down here, and it should be the same distance out. So look at this. This is 5 to the right and 3 up. Where do you think it's going to end up? Could that be it? Let's check it. Nope, too far down. Okay, so it's not 3 left and 5 down. Where did it end up? 5 right and 3 up. Let's see. 5 left and 3 down. Is that it? Yeah, there it is. So maybe you can see a relationship among the numbers here. Let's try another one. 270 about each point, 270 degrees about the origin clockwise. So we're coming this way. So let's take this one. It's going to go 3 times 90. So it's going to go 90, 180, 270. So that one should end up there. And where's this one going to end up? Can you predict where it's going to be? So let's do it a little bit at a time. So this is going to end up right and up one. It's going to go right one. It's going to end up here. Right, that's 90 degrees. And then we go another 90 degrees. There. Oops, there. Another 90 degrees. It's going to end up, let's see, does that look like the right way? Yeah, I think that's it. Let's check it and see. Good. And again, you might look at the coordinates there and see what that does to the coordinates here. Like this was 0, 6, it went to negative 6, 0. This was 3, 7, now it goes to negative 7, 3. So if you look, can we make a conjecture about where they might go? Well, it looks like the x coordinate here is becoming the y coordinate over here, And the y coordinate here is doing the opposite of it, becomes the x coordinate here. So that's an interesting thing there. So again, you can experiment with these. You can get new angles and just experiment with more and more of these. I'm going to leave it to you to experiment with those. The more you experiment with these, the more you're going to learn from them. Here's another one. Okay, exploring triangle rotations on the coordinate plane. So a triangle is going to rotate to a congruent image of a triangle. A rotation is an isometry. Okay, and we can see what has happened here. So which way did we go? See, we're starting with the one up here is the pre-image. The one that's shaded in is the image down here with the primes. So which way did we rotate? Well, we rotated clockwise by 90 degrees, or in other words, a negative 90 degrees. And that's about this point here. That's clockwise, and that's 90 degrees. So we can select these to see what's going on here. Let's see which one's the pre-image. Okay, looks like we're going around this way, which is clockwise. So we want to check clockwise. But it's not, yeah, it's 90 degrees there. Okay. And we can experiment with different ones, different rotations, clockwise and counterclockwise. Okay, so again, you can experiment with those on your own. See some interesting things. Here's another one that's similar to that. So here's a similar thing. This time we have to pick where the center point. So the center point looks like it's right here. Looks like that's the origin. So we can enter that in. Looks like it's rotated. Let's see, we're going this way. That's counterclockwise, positive direction. And what angle are we looking at? That looks like a right angle there. So that's going to be 360 degrees minus 9. That's 270 degrees. Let's see if that checks out. It says correct. And I can rotate. You can see it in motion dynamically. So notice one thing about this transformation stuff is it can really think of things dynamically. Here's another example. Again, you get to pick the things and try it out. Again, I'm going to leave it to you to check these things out on your own a bit. Here's one more I want to show you before the end of this video. This one is another one of Tim Brzezinski's. He does some great work, as does the GeoGebra team. And we can see some rotation going on here. So what you're supposed to do here is he's given you a tool set here. Notice he was able in GeoGebra to create a custom app here where he customized the toolbar set so that it's only just the basic transformations. There's a transformation for translation. Let's see, create a vector, translate it by the vector, rotate by an angle. Measure an angle, rotate about a point, and then reflect about a line. So just using those things, the question is how can we get one image to the other? So there might be more than one way we could do that. For example, we might do it this way. We might go from here to here and then say translate that figure by that vector. Now we could rotate. Let's measure an angle here from here to here to here. And let's see if this is going to work. We may have, that's going around the long way. Let me try that again. Let's rotate. Yeah, that's fine. I think that's going to work out. Let's try that again. From here to here to here. And then rotate uh, this object about that point, and then the angle by that angle. Let's see, what angle is that? This is angle epsilon. Rotate this about this point by the angle epsilon. And sure enough, that landed where it's supposed to be. So the idea is to try to get the figure from one to the other by some combination of these things. There may be a different way to do it. You might be able to do it. Well, I guarantee there's more than one way to do it. So you try to maybe see what's the easiest way to do it. Can you do it just using reflections? Can you do it in one single transformation? Can you get it just with some translation or rotation or reflection? Does it take more than one? Uh, can you list those together? Okay. And finally, the activity that I've introduced in an earlier video, you can see here for the one that I made for introducing transformations. And it talks about all the 5 basic types of transformations, talks about how you can do them with compass and straight edge, talks about fixed points, algebraic formulas. It really covers a lot of ground, and it shows you that. And I've introduced that in an earlier video. So this gives you several different GeoGebra activities, this one that I did here, but then several others as well that can help you explore different types of transformations, particularly translations.